In section 2.2, we're going to introduce the idea of the derivative, specifically the derivative at a point. So in this section, we're going to understand the concept of average rate of change and instantaneous rate of change. We're going to introduce the derivative, and we're going to think about estimating derivatives numerically, visualizing derivatives as the slope of the tangent line, and finding derivatives algebraically. Note that this is going to be very similar to section 2.1. We're just giving it a different name now, thinking about derivatives. And finally, in this section, we're going to learn the equation of the tangent line and go over some examples about how to find the equation of the tangent line. So this section is very similar to section 2.1, so let's do some review of those topics. We're going to let f of t denote the position of an object at time t. And we learned that the average velocity on the interval a to b, which is just another way of saying from t equals a to t equals b, is f of b minus f of a over b minus a. And graphically, we learned that the average velocity is the slope of the secant line connecting the points a f of a and b f of b. Then we use the average velocities to figure out the instantaneous velocity at t equals a. And we learned that this is going to be the limit as h approaches 0 of f of a plus h minus f of a over h. We also talked about an equivalent definition of the limit as b approaches a of f of b minus f of a over b minus a. We're not going to use that definition as much because it's not as nice algebraically. The one with h, even though it may look more complicated, is going to be nicer to work with. Finally, we learned that in the graph, the instantaneous velocity is the slope of the tangent line instead of the slope of the secant line at the point a f of a. So the big point of this section is to now give some terminology to this idea of average velocity and instantaneous velocity in general, as not every problem we're going to do is going to necessarily relate to distance and position and time. So first, we're going to use the terms average rate of change and instantaneous rate of change instead of average velocity and instantaneous velocity. And again, this is to give us a nice general cover of any problem that we could do. We can now deal with functions in general that don't have an application, or we can think about a function that might represent something else. For instance, we might have a function that represents money, and then the derivative, or the average rate of change, is going to talk about the change in money over time, nothing to do with velocity. Then we're going to define the derivative of a function at x equals a as the instantaneous rate of change at x equals a. So those terms are just interchangeable, they're the same thing. Which means that the derivative is going to be the slope of the tangent line of the function at x equals a. Then a piece of notation, we have that the derivative is going to be denoted with f prime of x. The apostrophe we're going to call a prime. This is called the prime notation. F prime of x represents the derivative of the function. Finally, we have a new definition of differentiable. So a function is differentiable at x equals a if the limit, this is the limit that is equal to the derivative at f prime of a. If that limit exists, then the derivative exists, and we call the function differentiable at that point. A lot of times we think about the idea of differentiability as very similar to continuity. So you can be continuous at a point, you can be differentiable at a point, and then a function can be differentiable in general if it's differentiable at every single point. We'll talk about differentiability later in this chapter. Finally, in this section, we're going to go over the equation of the tangent line. So we need some review from algebra, and that is the equation of a line in point-slope form. Using slope-intercept form is not going to be very helpful here. Point-slope form is going to be the nicer one. So this form is y minus y1 equals m times x minus x1. In this equation, the point x1, y1 is any point on the line, and m is the slope of the line. So the big point of learning this form is that if you want to find the equation of any line, all we need is two pieces of information. One, any point that lies on the line, and two, the slope of the line. We think about this graphically. If we know any point that lies on the line, and we know the slope of that line, then we are able to draw the line. We know it has to go through that point, and we know the slope. You can use the slope to find another point, and 2 points determine a line. There's a lot of different ways you can think about it. So for the tangent line, we need a point that lies on the line, and we need the slope of the line, and we have both of those pieces of information. We know that the point a, f of a, is going to be a point on the line that has to match the function at that point. And then the big thing in this whole section is that the derivative is the slope of the line, the derivative at a. So therefore, the equation of the tangent line at f of x, at x equals a, is going to be y minus y1. In this case, a is going to be x1, f of a is going to be y1, and f prime of a is going to be the slope. So we have y minus y1, y minus f of a, equals the slope f prime of a times x minus a. Note that we need both y and x in our equation of a line. Think about any equation of a line that you know, y equals 2x plus 5. That equation has both y and x still in there. So we're not plugging in for x, we just have a in there for x1. If we move the f of a over to the other side, we get the equation we're more familiar with, y equals f of a plus f prime of a times x minus a. If we think about this in a graph, we have our function here, f of x. We have our point a. If we want to find the tangent line, we're going to start with this special point a, f of a, the point on the line. And then the slope is determined from the derivative, the change in the function at that point.